Welcome back to Solutions. In part 4B of these videos, we're going to be talking about KSP some more. This is just a continuation of the last video. Now we're looking at a couple of other examples from your notes. Alright, a solution is prepared by mixing 100 milliliters of 1 times 10 to the negative third molar calcium nitrate and 100 milliliters of 1 times 10 to the negative third molar sodium fluoride. The question has to do with whether or not calcium fluoride precipitates from this solution, but there's a lot we have to do before we can get to that point. So first of all, let's look at the equation that's there on your paper. Calcium nitrate plus sodium fluoride is going to make calcium fluoride and sodium nitrate. And let's go ahead and balance that. But that's actually the least important equation that we have going on, even though that is what we're reacting. Let's first look at just the calcium nitrate part of this, the 100 milliliters of the 1 times 10 to the negative third molar. So just the calcium nitrate part. So when I made that calcium nitrate solution, 100 milliliters of that molarity, essentially I dissolved it in water and put calcium and nitrate together. So if I had 100 milliliters of this 1 times 10 to the negative third molar calcium nitrate, how many moles of calcium and how many moles of nitrate are actually in my beaker? Well, since you've got molarity and volume, 1 times 10 to the negative third molar is some number of moles divided by 0.10 liters. So we're going to multiply that, and we end up with 1 times 10 to the negative fourth moles. Which means 1 times 10 to the negative fourth moles of calcium nitrate were actually in that beaker to start with. And since it's a 1-to-1 ratio from calcium nitrate to calcium, that means that there's 1 times 10 to the negative fourth moles of calcium in my beaker to start with. And since it's a 1-to-2 ratio, 2 times 10 to the negative fourth moles of nitrate in my beaker to start with. So that's just in my first beaker, on the beaker on the left, what I'm going to mix. So let's look at beaker on the right, the sodium fluoride beaker. We've got the same volume and the same molarity, so a lot of this math is going to look very similar. But this time we have NaF. That's going to break apart into Na plus and F minus. There's 100 milliliters of 1 times 10 to the negative third molar. And so if you multiply it exactly the same way that we did over there with the calcium nitrate, you'll end up with 1 times 10 to the negative fourth moles of sodium fluoride in the beaker. Since it's a 1-to-1-to-1 ratio, that's really 1 times 10 to the negative fourth moles of sodium and 1 times 10 to the negative fourth moles of fluoride ion. So that's what's in my two beakers originally before I pour them together. So now imagine taking those two beakers and pouring those two beakers together. The volume is no longer the same. We started with 100 milliliters of each, now we have 200 milliliters total. So if I wanted to find the concentration or the molarity of my calcium and nitrate and sodium and fluoride, now I'm going to take my moles divided by my new liters, which is 200 milliliters or 0.2. So I'm going to take all of those numbers and divide them by my new volume. So I can find a new molarity. And when you take 1 times 10 to the negative 4 divided by 0.2, you end up with 5 times 10 to the negative 4. And the same thing down here for the sodium and fluorine. 5 times 10 to the negative 4, molarity. 5 times 10 to the negative 4 molarity. And then 2 times 10 to the negative 4 divided by 0.2 is 1 times 10 to the negative 5 molarity. So that's kind of initially what's in my beaker. Once I've mixed it all together, I have 200 milliliters. That's the concentration of each of my individual ions. Now this question particularly is asking about whether or not calcium fluoride precipitates. So since it's only looking for calcium and fluorine, technically, all I really needed was this and that, the calcium and the fluorine. I don't actually care about the sodium and the nitrate, because the question's not asking about the sodium and the nitrate. So 5 times 10 to the negative 4 moles of fluorine, 5 times 10 to the negative 4 moles of calcium in a beaker. Does these ions precipitate into a solid, or do they stay together? Sorry, precipitate into a solid, or do they separate into ions? So I cleared my screen so I can kind of see it and focus better. Let's see, I had 5 times 10 to the negative 4 molar calcium ion, and there was 5 times 10 to the negative 4 molar fluoride ion. That's what we had figured out before. That was what was in my beaker. So the original question, let's going back to the original question, will calcium fluoride precipitate? So there's a reaction that has to do with calcium fluoride itself. We know that calcium fluoride is made from calcium nitrate and sodium fluoride. So if it precipitates, it'll stay like CaF2. But if it dissolves, it'll turn into Ca plus 2F minus. So the question really is, this reaction, CaF2 going to Ca plus 2F minus, does this reaction happen, or does it not happen? Will it shift left, or will it shift right? So going back and putting in the numbers that we had from earlier, 5 times 10 to the negative 4, let's see if I can make that a prettier negative 4, molar calcium, and 5 times 10 to the negative 4 molar fluorine. And from here, once we've mixed these two things together, we're going to figure out whether the reaction is going to shift left or right. If you remember, to determine if it's going to shift left or right, we're kind of looking at Le Chatelier's principle, or maybe we're even looking at reaction quotient, that is Q, and in this case Qsp, since we're talking about Ksp. Remember that Qsp is, or Q in general, is the at any time constant, where K has to be the equilibrium constant. Since the 5 times 10 to the negative 4 molar is what we poured in our container to begin with, in this case the Qsp is my initial constant. It's solved the exact same way as Ksp. That's Ca plus 2. Okay, let's look at one more problem that's very similar to the problem before. Actually, this one's even a tad bit simpler. A mixture is formed by adding 50 milliliters of 1 times 10 to the negative 2 molar copper nitrate to 200 milliliters of 1 times 10 to the negative 4 molar sodium chloride. Will the copper chloride form? So let's write an equation. This time I'm going to write it all out. I'm not going to do as many steps as I did quite in the problem before. We have copper nitrate, and this is copper 1 nitrate, so it's just CuNO3, and sodium chloride. And it's going to make copper chloride, copper 1 chloride, and sodium nitrate. And so let's look at the copper nitrate first. 50 milliliters, which is really 0.05 liters, and 1 times 10 to the negative 2 molar. So if we do 0.01 molar times 0.05 liters, hopefully you find 0.0005 moles of copper nitrate. So that's the copper nitrate part of it. Let's look at the sodium chloride part of it. The sodium chloride part of it is 1 times 10 to the negative 4 molar times 0.2 liters, and that is 2 times 10 to the negative 5 moles. Just like in the problem before, we're going to divide that by the new total volume to find the new molarities. So those were my initial beakers, but I'm mixing them together, so now the concentrations are changing because the volume's changing. So I'll divide them both by 0.25 liters, because 250. And when I do that, I'll get a new molarity of 0.0005 0.002 molar for the copper nitrate, and 8 times 10 to the negative 5 molar for the sodium chloride. So that's just to start with what is originally in my beaker. So the overall reaction that we're actually looking for is, does copper chloride form? So that copper chloride, the question is it stuck like that, or is it going to turn into copper and chloride? So let's write that nicer. Copper chloride, which way is it going to go? To Cu plus and Cl minus, or is it going to stay at CuCl? Now we know from earlier that there's 0.002 molar copper ion, and we know from earlier that there's 8 times 10 to the negative 5 molar chloride ion. So we're going to use those numbers in my Qsp expression to figure out what this reaction is going to have to do to get to equilibrium. So Qsp is equal to Cu plus times Cl minus. So this is equal to 0.002 times 8 times 10 to the negative 5. All right, I've set it up that far for you. I want you to, on your own, finish calculating Qsp, compare it to Ksp, and decide whether a precipitate will form. Do that right now by yourself. So hopefully you did, and hopefully you got Qsp to be equal to 1.6 times 10 to the negative 7. And if we want to turn that into a fraction, that's over 1. And Ksp, because it's given in the problem, is 1.8 times 10 to the negative 7. And if we want to turn that into a fraction, it's over 1. And the reason why we might want to turn that into a fraction is because Q and K are really just ratios of products to reactants. So it's easier to see what's happening to the products or to the reactants if we look at it as a fraction or as a ratio. So Qsp is what I put in my beakers, Ksp is what it's going to end up coming to. How can I get the products to change from 1.6 times 10 to the negative 7 to 1.8 times 10 to the negative 7? Well, I see that this number is going to have to go up, and this number relates to the products, so the products are going to have to increase. In my reaction, CuCl makes Cu plus Cl minus. Since the products are going to have to increase, the reaction is going to have to shift right. So Qsp is smaller than Ksp. That means, therefore, the reaction will shift right towards the ions, not left towards the precipitate. Since it's shifting right towards the ions and not towards the precipitate, then that means that no precipitate will form, because the reaction is going to be spontaneous in the forward direction instead of the reverse direction. All right, well, that was just a little bit more examples of Ksp problems. I hope you join me next time for the common ion effect.